Good morning, everyone. Let's start the class. So today we're going to start a new topic, right, called discrete choice models. Again, that one can be viewed as an extension of that binary response model that we talked about previously. So binary response model, recall that the setting is that we have this y variable, right, which takes one value out of two possible values. Okay, so then we have 0 and 1, right? Two possible outcomes. Then this y value, this response variable, takes either one of this value, but only one. But think about that. What if we have more than two possible outcomes? And each individual has to choose one out of these several alternatives, right? So this actually leads to this setting. Because if we have more than two, then the binary response model will not work. Right, then you cannot, we have, say, even if we only have three, right, then 0, 1, that's way to model that data. So we have to extend that setup so that we can accommodate the multiple. Okay, so actually this framework that we're going to talk about today actually serves that purpose. So under this framework, actually you can set this number of alternatives, number of options to any number. Okay, so you can have like 10 options, and then each individual choose 1 out of 10. That will work perfectly fine. All right. So, but later on, you're gonna see that actually the binary response model can be viewed as a special case of this discrete choice model. Okay. Of course, if the model can handle 10 options, certainly it will be able to handle 2 options. All right. So let's take a look at the setting. So like I said, the setting is just basically, each individual, right, needs to choose one option out of multiple options. And then, examples is abundant. I don't need to spend too much time talking about those examples, right? So the leading example, the leading application of multiple choice models is in the marketing domain. When consumers make choices between multiple brands, right? This is more than common. In reality. So the same product, the same category of products, you have a lot of different brands, right? Just as you walk into the grocery store, right? You see the same, the cereal, so many different brands, different options. Then eventually, consumer usually need to only purchase one. So then which one will consumer choose out of so many different options? That's a classical example, classical application of multiple choice models. All right. So then other, choices, similar or choices in all those different contexts. As long as it involves choosing one option from these multiple possible options, we can use this one. Right. So in the homework exercise, I like to choose this transportation mode. Right. So going to work, commute every day. Then what transportation mode you choose. Right. Here probably we don't have many competitive options, right? So usually driving is pretty much the only option, but in some cities elsewhere, right? So like in Europe, in Asia, you have very well-developed public transportation system. Then which transportation mode do you choose? Right? Do you take the subway? Do you you can ride a bike, right? You can drive a car. Then what choose? Of course, you have the trade-off, right? You have time, you have cost, right? You have convenience, all the trade-off. Then those will be the X variable, okay, affect your decision. And then eventually, we observe each individual's decision, and then we can think, okay, what is the possible choice? What factors will affect those decisions? And then, suppose that you will work for the the local government, right? So the public kind of planner, you want to say, study whether it's worth investing in a new public transportation system. Then you want to do the analysis, right? Then if this new, say, subway line is built, then how many people will be likely to switch to use this new public transportation? But those things, you need to build a model, right? So to model consumers' choice decision in order to say that what if a new option become available, then how many of them will switch? Right? Those are all the possible applications of this discrete choice. So very useful, right? Especially like I said, if you understand consumers' choice decision among those existing options, then you can come up with analysis about, so what if I offer a new option, a totally new option? Then how would the consumers change their choices? Right? Those type of implications you wouldn't be able to derive without modeling their decision process. Right? And discrete choice models is able to help us. Right? Of course, other examples in choosing between multiple, for example, you guys choose the MSA program, Georgia Tech, right? But when you apply that, there are a lot of programs available, and you may get multiple offers. Then eventually, choose to come here, what contribute to that decision, right? So those, we collect the data, we can try to model to see that, okay, what affects, students' decision in choosing, a particular graduate program. So a lot of examples. All right, so now let's, before we get into the model, let's talk about some basic features of this discrete choice framework. So here, when we talk about discrete choice, for this modeling framework that we're going to introduce, the choice set actually need to satisfy these properties. First of all those options are mutually exclusive. So what does that mean? That means each individual eventually only pick one option out of these many options. All right, mutually exclusive. The individual does not choose more than one option at the same time. So what we call usually is like they have unit demand of the product. Then you offer multiple products for each consumer to choose from. But each consumer only has unit demand. So they only want one. So they just only pick one out of this multiple choice. So this one may sound like a strong assumption, but actually it's not. Think about that. What if consumer have, in some context, a consumer is, or individual decision maker is allowed to choose more than one option? Can you do some simple transformation to make it still satisfy this mutually exclusive requirement? You can create additional options that consist of, say if a consumer can choose up to 2 options, then you can create an additional option that consists of any 2 options available, right? You artificially create those multiple, new options, and then, then we can restore this exclusive, the mutually exclusive property, right? So then eventually consumers still pick one out of all those options that we have, but you just create additional options. All right, so that's the first requirement. Second requirement is the choice set need to be exhaustive. Again, exhaustive means it covers all consumers' options. Basically, each individual has to pick one option out of all the options in the choice set. The choice set covers all options individuals face. All right? Again, this may sound like a strong assumption, right? So then what if, consumers can choose options outside this choice set? But again, we can easily transform that so that this exhaustive requirement is satisfied. If you have 5 options, but consumer can choose options other than those 5 options, what can you do? Exactly, you add a so-called outside option, right? So anything else other than the 5 options that we observe here, then we add this outside option as the 6th option in the choice set. Then this requirement is satisfied. Then the consumer has to pick one, out. Alright, so these 2 options are not really strong. These 2 assumptions are not really strong enough. And these 2 assumptions together, that means each consumer has to pick one, but only one option out of all the options in the choice set. So finally, the last assumption is actually a real assumption. So the number of options need to be finite. All right, so discrete choice model can only handle finite number of options. So you cannot have infinite many options in the choice set. Then discrete choice model won't work. Right? Actually, for the finite one, theoretically, any finite number it will work. Right? Theoretically, for the model, there's no problem. Any large number of options will all work as long as it's finite. But practically, later you're going to see how the model is set up. Practically, you don't want the number of options to be too large. Too large, the model is, too cumbersome, like too much computation will be needed and it won't work very well. Okay, although theoretically there's no problem, but practical. So that's why discrete choice model works especially well if you have like a, reasonably small number of options in your choice set. All right, so I would say like 10, around 10, less than 10, it works perfectly fine. But if you have like hundreds of options in your choice set, it's a little bit hard, be practical. So that's why, when you actually apply discrete choice model, you may want to think about how you should kind of format your choice set. If you have too many options, you can combine some options, right, into some categories, and basically just choose between those several categories. That will work better. All right. So in that sense, the last assumption, last property is something to pay attention to. All right. So these are the requirements for the choice set. So once these requirements are satisfied, and then we can just apply the discrete choice model to model consumers' choice decision, for choosing one option out of all the options in the choice. All right, so let's see how it's modeled. So the discrete choice model is still based on this utility function. So this so-called random utility modeling framework. So utility function, utility is a concept, is a basic concept in economics. Are you guys familiar with that concept? As long as you learn any economics, okay, you probably in the first or second class you're gonna be introduced with this utility function, because all those economic theory is based on utility function. Each consumer, right, derive a certain utility from taking a certain action. Okay, each individual decision maker derives certain utility from taking a certain action. And then their goal is to maximize their utility, okay, by choosing the action among all the possible action set. By choosing the action that will maximize his or her utility. Okay, so utility is just like the value, right, individual can derive from taking a certain option, from taking a certain action. Now here, that's the same. There are certain options, several options in your choice set. Then each option, by choosing each option, an individual can derive certain utility. Okay? And then eventually the individual will choose the option that will give him or her the highest utility among all these options in the choice set. So that's the basic framework. Alright, then how is the utility derived? So you see it's modeled this way, two parts. Okay? So Uij, I is the index for individual consumer, individual decision maker. J is the index for option. All right. Here in the discrete choice setting, we often call those options alternatives. So J is for the J's alternative, right, in the choice set. So Uij simply means the utility individual I can derive from choosing J option J. Right? Very, very straightforward. And then this utility is defined as the sum of two parts. Okay, it can be decomposed into two parts. The first part is Vij. This Vij is what we call the indirect utility. Indirect utility, this is basically the deterministic part of the utility of Uij. Okay, so this is the Vij is also the part of the utility individual I can derive from choosing option J, from choosing alternative J. But it's the deterministic part. So this part, this later will be modeled as function of all those x variables that we observe in the data. Okay, so it's modeled as, you can think of it as like the usual linear combination of x and the coefficient beta. So that's the determinant, so that's the observed part. So based on all the, because for each individual option combination, right, we observe the data, we observe some data, some attributes of all those different products, different options in the choice set. And then we observe data information about individual as well. So some x variables will be about individual, some x variables will be about the products, the options. Right, so anyway, those will all be the x variables, and they will all enter this Vij. Alright, Vij is the observed part of the utility individual I can derive from choosing option J. Okay, so that's the idea. And but as usual, we also have this epsilon ij in addition. That one is the unobserved part. So this one is the error. All right, error, the random variable, the random part. So beyond that, we still, beyond what we have observed, what we can kind of say, there's still something that we do not observe that will affect consumers' decision, affect individuals' decision, right? So will change individuals' utility. So those things that we do not observe. So all we can do is just to model that as an error, as a random error. So that is represented by this epsilon ij. That's the random perturbation, right? Random error for the utility, that will affect the utility of individual I from choosing alternative J. So this is epsilon ij. All right, so then the combination of these two, the Vij, the observed part, and the epsilon ij, the unobserved random error, combined will determine the individual I's utility from choosing alternative J. All right, then once we have that, then eventually how will individual make choices? Then that's very straightforward. The individual simply choose, individual I, right, derive different utility for choosing each option, right, within the choice set. Then eventually individual I simply just compare all those different utilities from choosing different options and pick the option that will give him or her the highest utility. So that's the choice decision. So this is the choice decision. So we can derive the so-called choice probability. This is the most important part of this model, the choice probability. This is just equivalent to the probability of success, right? We have derived in binary response model. I remember in the logic model, right? Binary response model, we derived that probability of success. So this is similar, right? Probability of choosing a particular alternative. So the choice probability Pij simply means the probability of individual I choosing a particular alternative J. But here, pay attention here. This Pij simply means the probability of individual I eventually choose alternative J over all the other alternatives. All right? It's after comparing all the alternatives, eventually this individual I choose alternative J over all the other alternatives. So in deriving this choice probability, all the comparisons are already included. It's after all the comparisons, after comparing all the utility from all the alternatives in the choice set. Okay? So eventually, this individual picks a winner. That is alternative J. Okay? That's the probability. That's the probability for alternative J to become the eventual winner for individual I. That's what the Pij is derived. Okay. So now, based on that definition, how can we, based on the model setup, how can we derive the Pij? Just follow the decision process, right? So just this individual I simply just compare the utility from all alternatives and just pick one. So the probability he or she eventually picks alternative J is equal to the probability that this Uij, the utility from the J alternative J, is greater than the utility from any other alternative in the choice set. So Uij is greater than any other Uik for any k not equal to J. Right? So again, like I said, here we are actually doing multiple comparisons. For this Uij to compare with all the other, let's say totally we have this capital J number of alternatives in the choice set. Then this probability actually involves J minus 1 comparisons. Okay, comparing this chosen alternative little j to any of the other J minus 1 alternatives in the choice set. And it has always need to be greater than that.
I know that you're distinguishing utility from probability. Can you explain more about what utility is? I don't have very strong economics background.
Utility is the value. Probability is it's totally different. Utility is the value you can derive. Probability is Probability is the chance that the utility from this option will be greater than the other option.
So it's the thing that you choose. That's what utility is?
No, it's the value you would derive from choosing this option.
Okay.
All right, this is the level of satisfaction, for example, you can derive from choosing this option. That's utility. Okay, so that's the probability, the choice probability. Again, includes all the j-1 comparisons. Then we can just simply, how does the comparison? We can simply just substitute in those definitions, right? So then the probability is this Uij is a Vij plus the error term, and this Uik is Vik plus the error term. So now think about that. Where does this why do we have this probability? Where does the probability come from? Why do we have the probability? Why isn't that deterministic for a consumer to choose which one? For example, when you choose something, you know, right? You are presented with 10 options. Then you look at these 10 options, you know which one I should choose. Then, but why do we have this problem? Why is like that? Because the choice probability simply means the choice is uncertain. I don't know. You know, for I don't know which one I will choose. I could choose this, could choose that, could choose that. So why do we have this probability? Why isn't that deterministic?
It's based on preferences. Different people can choose different things.
Yeah, different people, but it's for a particular person, even an individual I. But why do we still have that probability?
Information is imperfect.
Imperfect. Which part is imperfect? Which part is?
The individual does not know the utility before they make the choice.
Is that true? Yeah, that's a good point. But be careful. Is that a statement correct? Yeah, it's one possible understanding, but we make sure that this actually is not the you know what we are modeling here. All right? Does individual know his or her utility from choosing each of the options? Actually, each individual knows. So the choice for each individual is actually deterministic. It's just like you go to the store, right? You look at all those products. Eventually, you know which one to pick. You do the comparison. You know, so you actually look at the product, the feature of those products. You come up with your own decision. You have your own evaluation, right? So how much utility I can derive from this option, how much utility I can derive from that one. Then after comparing, you pick up the one that gives you the greatest alternative. So you know that. So for each individual, actually there is actually no certainty, no uncertainty. Okay, he or she knows the utility he or she can derive from each alternative, and then eventually he or she just pick the alternative that will give him or her the greatest utility. But here, for why does this choice probability come in our model? That's to us, we do not know. Which part we do not know? The error term. All right. So the error term is the unobserved part of the utility, but it's the unobservable to whom? Exactly, to us researcher, to us analysts. You do not observe. Individual himself, individual I, him or herself, knows this error term's value. All right. So as a result, the individual I knows Uij, but to us we do not know. All we know is Vij because that's what's observed in the data. But the Uij, that's in addition to what's observed in the data. Each individual has their own consideration, their own the preference. That is not captured by the data, so it's not known to us researchers. So that's why to us, each individual's exact preference, there is variation beyond what can be observed in the data. So that's the idea. So this choice probability actually comes from this error. Again, that's the uncertainty to us researchers. Okay, we do not know. Okay, given what I can observe about the products, about the features of those products, I can say that what the probability of this individual choosing this item is this much. Because I cannot be sure, because each individual still has its individual preference, which is beyond our observation. Is that true? So mathematically, the probability actually originates from the presence of this error term. Because again, the error term is modeled in the usual way as a random variable. So its value is random. It's the random realization. So depending on its realized value, so Uij could be greater than Uik, but could be less than Uik. So all we can say is that probability for Uij to be greater than Ui.
So the error term is just something the steer manager doesn't know, but the user, the individual always knows.
Exactly. The user, the individual I observe the realization of epsilon ij. All right. But what happened to us is we do not observe the realization of epsilon ij. We only know the distribution of epsilon ij.
And B, the representative B, that's always deterministic.
That's determined. That's the later on. That's modeled as a function. That's like a linear function of all the x variables with the beta coefficient. But what we want to do is the coefficient is not known. It's deterministic, but it's unknown, right? So what we want to do is just figure out the coefficient value. Is that clear? So make sure you understand the setup correctly. All right. Epsilon ij, this random part, it's random, so it's not known. That realize the epsilon ij is not known to us. It's not directly observable to us. All we know is the distribution, the overall distribution. But Uij is actually observed by each individual I. So they observe Uij and they make the choice. So the choice to each individual I is deterministic. But to us, it's probabilistic, and the choice probability is determined by this value.
One more question. I'm wondering for the individual I, what if we have a time? For example, like the individual choosing the alternative.
Yeah, that's a good question. But yeah, we could define the tie-breaking rule, but actually here tie doesn't really matter because this one is continuously distributed. So the probability of epsilon taking each exact value, the probability is 0. Is that understandable? Because this epsilon is continuously distributed. So the probability for two alternatives to tie is 0. The probability measure is 0. So that's why it doesn't really matter. You could define the tie-breaking rule, but it doesn't affect the choice probability. Okay, if it's discrete value, then there's for certain value there's always a probability mass. But for continuously valued random variable, right? So the probability for that random variable to take any exact value is always 0. So that's why tie-breaking rule here it doesn't really matter. Yeah, you can think of like a tie-breaking if the two utilities ties, the individual just randomly pick one out of the two alternatives that's tie in terms of utilities. But again, the probability of that is always 0, so it doesn't really matter. Doesn't affect the choice probability derivation. Okay. Now back to this question. Choice probability, right? So it's equal to this. So you see, the source of this uncertainty is this error term. So we can further derive that. So this choice probability of user I eventually choosing J over all the other alternatives is equal to this. We can derive that. That's the choice probability, the difference between any pair of errors, right? Less than the difference between the V, the observed part of the utility, the indirect utility function. Okay? So that's this one. So then how can we derive that choice probability? Apparently it depends on the distribution of the error that we'll assume. Okay? So depending on what we assume, what distribution we assume for the error, we're going to have different type of discrete choice models. Just this is exactly like the case of binary response model. Remember, binary response model, what model eventually we are applying depends on what assumptions that we are assuming for the error term. Right? If we assume error term follows logistic distribution, we got the logic model. If we assume error term follows the normal distribution, we get the program model. That's exactly the same case here. Okay? What distribution we should assume for those error terms actually will determine what type of discrete choice model we are getting. Actually, for discrete choice model, because of the complexity, because now we have multiple choices, so actually there's a lot of different ways to specify, to assume the distribution of the error term. And a lot of different ways to make those choices correlated across each other. Okay, so that's why discrete choice model is a very rich area. Actually, it's even an active research area, still like a new method, a new way of estimating those models, new applications of this model are being developed. Alright, so yeah, if any of you are interested, this is also a very powerful way, like a modeling framework, and it's a very, it's a modeling framework that can be widely applied. So that's why, if anyone are interested in this topic, I actually strongly encourage to kind of delve deep, into this one. You can easily take like a semester-long course introducing discrete choice modeling. Right? There are like books dedicated to discrete choice topic. Right, so but just let you know that we can do logic and probing, but of course then the distribution will be slightly different because now we are dealing with the so-called multivariate distribution. Right, so now you have multiple options. Then each option has its own irritant, but these irritants could be correlated, could be assumed to be independent from each other, but could also be correlated. Right? If that's the case, then you can, using those so-called multivariate normal distribution, then you can introduce correlation across the irritants of different alternatives. Okay, so the model can be made very complex. Okay, anyway, we're gonna focus on the standard version, okay, the most standard version. So we will assume that this irritant is so-called IID. You guys familiar with IID concept, right? So independent and identically distributed, IID. Alright? So each epsilon ij is IID. So each epsilon ij is just an independent random variable, independently realized, and they follow the same distribution across all epsilon. So that's the simplest set. Now, what distribution do we assume for this epsilon ij, which are IID, right? The common distribution that we assume. What is the distribution we assume? Actually, the standard, most common form of discrete choice model. Actually, we'll assume this epsilon ij follow the so-called type 1 extreme value distribution. As a different distribution. All right, not normal, not logistic. It's a type 1 extreme value distribution. So now, how does this distribution look? Again, like we said, for each distribution, we need to specify its, one of the two, right? So the PDF and the CDF. As long as you specify one, the other can be derived accordingly. So for type 1 extreme value distribution, the CDF, the PDF can be written this way, and the CDF can be written this way. That's a little bit weird distribution. A lot of E. Here, this E is again the usual exponential function. All right, that constant, the 2.7, that constant, the usual exponential function. So it's E to the negative E to the epsilon. Epsilon is the random variable, the focal random variable. Okay, so again, what does this mean? F of epsilon. Make sure you understand what. Again, if you are still not clear about the concept of a CDF and a PDF, be sure to review that concept. All right, so that's more than it's the basic of all those description of distribution. Basically, for each distribution, we have to define CDF or PDF. Again, this F of epsilon. Epsilon is simply just a random variable, right? So to help you easily understand, you can call it X. So it's the possible value of this particular random variable, the focal random variable whose distribution we are describing. And then here it's e to the power of x. So what does that mean? This measure the probability. Let me use again. Let me use this, okay, x0, right? So that it's clear to you. So it's the probability of this random variable being less than or equal to this particular value. That is equal to this number. All right, this is what this CDF function means. All right, CDF function simply means CDF function of a certain value simply means the probability of this focal random variable whose distribution the CDF function is describing this focal random variable being less than or equal to the given value. The probability is this much. Alright, that's what this F epsilon means. Alright, this epsilon is just a possible value of this epsilon. Okay, any possible value, given any, that's why I use x0 here. It's any possible value this epsilon can take. Okay, and the probability of this random variable, epsilon, being less than the given value is equal to this much. This is the CDF function. So once you know the CDF, this CDF function is for any possible value. Right? For any possible value, I know the probability of this random variable being less than that value. Then if I know that this whole function, then I know the whole distribution. Is that clear? Because yeah, this is a function, so that if we know the function, we know the probability of this random variable being less than or equal to any possible value. Right? So that's why once this function is described, we know the entire distribution. Okay? And then the CDF function, the PDF function, the little f is simply this one, take a derivative with respect to this random variable. Okay, so you take a derivative of this guy with respect to epsilon, you get this one. Okay. Now, this is and this one gives you this type 1 extreme value. So type 1 extreme value distribution, why do we get this? Why do we come up with this distribution? Right, it's very weird. So why do we do that? Why don't we simply use normal? Well, type 1 extreme value distribution has, first of all, how does this distribution look? Here I plot this, this PDF. Again, PDF gives you the usual density distribution. So that's like the usual bell curve, right? You see for normal distribution. That is actually the PDF. And as have you worked on the homework 4, part 2, right? So I asked you to plot the density function, the PDF of that the duration distribution, right? And then later on I asked you to plot the histogram of all the durations you observe in the data. And then you can match these two, right? The histogram should be pretty much fit with the PDF that you plot. So PDF you can think of like it's roughly it's a histogram. It's the approximation of the histogram. Or it should be the other way. Histogram actually is approximation of the true PDF function. Alright, so PDF function basically is just a density function. It's just like the histogram. So that's why it's the usual bell curve. So now we can plot the PDF of this extreme value distribution. This is the PDF. Now take a look at this distribution. How does that look? Actually not too far away from the usual normal distribution. Right? Still roughly has this bell curve. But one key feature we can immediately notice is that what? It's not symmetric. Right? Unlike this normal distribution is perfectly symmetric. And it's symmetric around 0 and around the mean. But usually we'll just set the mean to 0, then it's symmetric around 0. But this one, you see, it's not symmetric. And actually, because it's not symmetric, so the standard normal distribution, the expected value is in the middle. And if we normalize that, the standard normal distribution, the expected value is 0. Right? But here, you see, it's not symmetric about 0. So the expected value of this extreme value distribution actually is no longer 0. Actually, it's positive to a certain constant. Right? And the variance of this extreme value distribution is this much. You can calculate that it's larger than 1. Okay? So in this sense, the extreme value distribution close to normal, but it's slightly asymmetric, slightly skewed. And it's a little bit fatter, a little bit of more widely spread than normal distribution, than standard normal distribution. Right? But that's it. That's all the differences. Other than that, generally speaking, it's still close to the usual distribution that we often assume. All right. So that's why first we'll let you know that what this extreme value distribution looks like. It's not too weird. It's not too strange. It's still quite quote unquote normal, right? Just slightly like a different from normal distribution. Right? So empirically, practically, it's hard to distinguish between a normal distribution and an extreme value distribution. In this sense, extreme value distribution, distribution-wise, the shape-wise, it's not like too unusual. Okay, that's the first kind of message for you to keep in mind. Second of all, then again the question, but why do we want to do that? Okay, it's not too weird. But why don't we simply just use normal? Why don't we want to introduce that? Why do we want to use that? Well, the reason is that, remember, eventually we want to derive the choice probability, right? We stop at this step because to further derive that, we need to know the distribution of the error term. So then, depending on what distribution we assume for the error term, we can further derive the choice probability. So, but the reason, we choose this is because this has very favorable analytical property. So if we assume the error term follows IID type 1 extreme value distribution, then we can further derive the choice probability as this. Alright, so the error term is this, right? So as we just derived that probability of I eventually choosing alternative J over all the other alternatives is equal to this, right? Then how do we further derive that? Again, this, like I said, involves J minus 1 comparison. So it's the, then we do the comparison. For each comparison, it means that the utility, right, from that option alternative K is less than the utility from alternative J. So we can write this way. It's the epsilon ik is less than this value. Right? So now, and then we do this choice of this for each alternative, right? Each K. So you see, for each K not equal to J, we have this probability. And then we have J minus 1 such probability. So we multiply all of them together. So that eventually will be the probability of alternative J being chosen over all the other alternatives. So for this one, we actually can derive that as we can explicitly derive that as this option. Right? But here, pay attention, the trick is now we have two random variables here. Right? This one and this one. So the trick is that we first fix this random variable, derive the probability for this random variable being less than this value. Okay, assuming that we know the value of this epsilon. Then what's the probability? Probability of a random variable being less than a certain value. What's that? Right? That's this guy. So once we know the CDF, the probability of this random variable being less than a given value is simply that CDF. So we already know the CDF following this one, so you can just write this one. You see, this guy, e to the e to the this one is simply just the probability of this focal epsilon being less than this value. Is that clear? That part is just the CDF. So that's why you need to know the distribution of the error term, the distribution that you assume for the error term, so that you can derive this problem.
I know that in CDFs you wrote the less than equal to sign, but that's just strict less than.
Yeah, then like I said, that because it's continuously distributed, so that exact value doesn't matter. You see, whether it's exactly equal to, or because the probability of that exactly equal to at any point is 0. So doesn't matter.
Is there an interpretation of what that is, like go back to the other alternatives, or what, is there any sort of meaning behind that first part, that likelihood?
Which part?
So yeah,
This one?
it's the CEF of EI.
This one?
You're trying to find EIK is less than all that, and EIK is the error of the alternative.
Yeah, this is from here, right? So here is this one is Uij, this one is Uik, right? In order for individual I to choose J over all the other alternatives, Uij has to be greater than any Uik, or any K not equal to J.
No,
And then you just do the transformation, right? So based on this, you do transformation so that it's centered around this epsilon ik, and then you can keep doing that.
Right, I understand what it is. I'm asking, is there an interpretation of what that likelihood is when you're multiplying them all together? Like that's the likelihood of picking
Yes.
the alternatives?
Yes, because for that comparison, again, we need to alternative j to be the final winner, we need to do j minus 1 comparison, comparing this j to any of the other j minus 1 options. And then this j has to beat all the other j minus 1 options. So that's why we need to do j minus 1 separate comparisons. And that outcome always have to be satisfied. So this j always need to be greater than all the other. That's why here we have j minus 1 comparison. So each comparison, again, for this alternative j to win, it's probabilistic because of the existence of the error term. So each comparison, right? So there's a certain probability for alternative j to beat the other options. Then we have j minus 1 comparison. So it's the product of j minus 1 probability. Okay. Why we simply do product? Because the IID assumption. Because we assume that the distribution is identical. So the probability of j beating alternative 1 and versus the probability of j beating alternative 2, they are independent from each other. Right? So then the chance of both happening is simply the product of the two probabilities. Okay, so that's how we derive the probability of two independent events. Is that clear? That's the basic of our probability, right? Two random events. Then if they are totally independent from each other, then the probability of both events happening is simply the product of the probability of each event happening. Right? That's the idea. So if the two events are correlated, then that's not the case. Right? Both events happening, that's more complicated. You need to incorporate the correlation. But here we assume, that's why we assume IID, that makes the whole expression much simpler. All right, two random events, right? Each random event happening, this probably is, say, its own probability. Then the probability of both events happening, if the two events are independent, the probability of both events happening simply equal to the product of the two probabilities. All right, the basics about this probability.
Okay, so the e to the power of minus all that is the probability of the CDF of each I and of each I and of each j.
Each j, yeah, each j. I is the individual index.
Okay, so why do we need to integrate it again?
That's a good question, yes. So I haven't finished that yet. All right, so this thing is what? The probability of epsilon ik less than this value, right? So that's the f, so that's where we get this. But you see here, we still have this epsilon ij, which is again a random variable. So its value we actually do not know. So that's why this integral is that we're gonna integrate out the possible value of epsilon ij. You see, this integral here is integrating out the possible value of epsilon ij. Is that clear? So in deriving this expression, we assume that epsilon ij is known. But actually we do not know, so that's why eventually we have to integrate that out. So when we integrate out, this is what? This is the PDF, this one, of that epsilon. So you see, this is the value of epsilon ij. So what we are integrating out is the possible value of epsilon ij. All right, that's how we are deriving this choice problem, because this choice probably involves two random variables. So actually, that's the trick we are doing. We first fix one. We assume that we know the value of the second random variable. So then the probability of the first random variable being less than that value can be written as the CDF function. But then still, we do not really know the value of the second random variable. So then we have eventually integrated it out. All right, that's the trick that we use to derive this choice problem.
And here, EIJ is one alternative. You're comparing it to one alternative or all of them together. Like you're saying EIK is less than EIJ, where EIJ is fixed, or all of them, like all of them compared to each other.
EIK is a random, epsilon ik is a random variable. We do not really know its value, okay? But we say that its if, we're deriving the probability of J being chosen. So the fact that J is chosen is equivalent to epsilon ij plus this has to be greater than this plus this. So that's why you have this comparison, this inequality. All right, but we do not really know the value, so that's why we're evaluating the probability. All right, the probability of this happening, this inequality being satisfied. But this inequality involves these two random variables, so that's why we need to evaluate this probability based on the distribution of these two random variables. So that's why we are deriving this form.
So if I'm understanding this correctly, you get to the integral by taking that probability, which is the CDF, and because CDF is the integral of the PDF, you're inserting the PDF and integrating this, and then you're just manipulating the math.
Yeah, this one is integrating over the possible value of this one. Okay, but this one, the first part is about the distribution of this one. Okay, first we assuming, like fix this one, assuming you know this one, then the probability of this epsilon being less than this value is this much. That's a CDF. But then we do not really know this second random variable's value. So that's why we need to do this integral. But this integral is integrating over the possible value of this one. So that's why we need to use this PDF. But this PDF, you see, the notation, it's about epsilon ij, not ik. Again, J is the chosen one. The chosen one, the alternative chosen by this individual.
I just like in general with discrete choice models, are we going to choose J and then always keep J the same? So we're comparing J to all K, but are we going to change J and then look at all?
But the J is the chosen one, so it's the one that we observe in the data. In the data we observe eventually what option each individual chooses. You see, you observe that this individual 1 chooses option 2, individual 2 chooses option 5. You observe that that's in the data, but you want to know that what's the probability of that. And eventually what we're going to do is still that maximum likelihood estimation. So then we want to find the beta coefficient so that we maximize the likelihood of the observed choice. All right, so that's why you first need to derive the probability of each individual choosing those alternatives. Then you can maximize the likelihood. All right, okay, so with this expression, then the rest is just the math. All right, so this is related to the model. So, but after this, you need to do a lot of the integral derivation. Right, so actually, it's a good. I encourage you to work on that. Actually, it's a good for you to review on how to do integral. This actually we do the so-called integral by parts. Change a variable. You change the variable and you play with that, and then you can keep deriving. So I'll skip that part. You can find that from any a book introducing those multiple choice questions. And then eventually, after a lot of derivation, a lot of the change of variables, eventually we arrive at a very neat form of equation. Actually, it's this whole complex integral actually can be eventually derived into this expression. So this is the choice probability, the probability of individual I eventually choosing alternative J over all the other competing alternatives is equal to this. All right, so again, you can forget about all this, right? This is just to help you understand where it comes from. But this, make sure you remember that. This is the choice probability of the discrete choice model. This is the essence of discrete choice model. The probability of individual I choosing alternative J over all the other competing alternatives in the choice set is equal to this much. Now make sense of that. What is that? Again, here this E is the exponential, the usual exponential function. It's what? Exponential of Vij. What is Vij? The observed part of the utility, right? By individual I from choosing this alternative J, from choosing this chosen alternative J. Okay? And divided by what? Sum of E, V, I, K, of all K. Alright? So in other words, it's the, you can write it just e to the vi1 plus e to the vi2, e to the vi capital J. All right? This is the denominator. Now, does this make sense? You see, this equation, this result actually is very, it's very intuitive, right? It makes total sense. So e is that you can sort of ignore the e. E is just exponential function, it's an increasing function, right? So if the Vij is large, e of Vij is large. If Vij is small, Eij is very small. So for you, to understand that, you can for now you can temporarily ignore this Vij. So roughly, what this choice probably says is that the probability of choosing a particular alternative over all the other alternatives is simply equal to the ratio of these chosen alternatives that observe the utility compared to the sum of the observed utilities from all alternatives. Right? So depending on how much, right, how significant this alternative is, then the probability of this alternative eventually being chosen, will be proportional to that.
Will it be the proportion Vij to all the other alternatives?
Not all, everything, including itself. Including itself. Alright, so say if Vij, right, so this particular alternative, the Vij, the observed utility, indirect utility from that alternative is very large. So then this alternative's probability being chosen is also large. If it's among all the other alternatives, it's relatively small, then the probability of this alternative being chosen is also relatively small. And also now think about that. If we add up the choice probability, this is a Pij, right? If I add up the choice probability, Pi over all possible j, what does that add up to? Or j from 1 to big J. Exactly, add up to 1. It has to add up to 1. Right? The probability of choosing one is this much, rather than choosing the other is this much. But if we add up all the probabilities, it has to be equal to 1. Because, again, that exhaustive assumption. Right? So each continuum has to choose 1. So then the sum of all the choice probabilities has to be equal to 1. And mathematically, we can easily see, right? It must be equal to 1. The denominator is the same, then the numerator add up. So it's 1. Alright, so add that up is equal. So that's why this equation, this expression makes total sense. Right? So when I first saw that, I see, yeah, it's beautiful, it's neat. You see, it's very neat. It's it's not like we just abruptly assume this expression. Right? It has this like a theoretical foundation. We can derive everything, right, from this theoretical the framework. But eventually we arrive at this very simple expression. Right? Once I showed you this, once you understand where it comes from, you can forget all of the theoretical derivation and you can directly use this expression, which is very neat, very simple, and makes total sense. Alright, so that's why this, you see, this is only possible, we get this from that assumption that the irritants follow that extreme value distribution, the hyper extreme value distribution. That's why this extreme value distribution is so useful. Right? Because of that, we'll be able to, because we have this, these are all from this extreme value distribution. If we don't have that, we will not be able to have such a neat expression. Alright, so that's why it's so actually it's, kind of creative, right? So when this distribution is first kind of introduced and this, kind of used, because it's, it's a distribution of kind of man-made, right? So because, people kind of figure out that if we use this distribution, we can arrive at this, and then, then just, come up with distribution, give it a name. All right, but like I said, this distribution, empirically, practically, it also makes sense. It's not too weird. It's not too different from the usual normal distribution. So that's why it's reasonable to assume, the irritant follows its distribution, right? And analytically, it gives us such a greater convenience. So that's why it's the most commonly used for discrete choice. And this type of model, okay, assuming Ayrton follows this extreme value distribution and with the choice probability derived as this way, it's called multivariate logical multivariate logical model. Why it's called a logic model? Think about that. How does this connect to our usual logic model from binary response model? Recall, what is the choice probability? What is the probability of success in binary logic model? E to the x beta divided by 1 plus e to the power of x beta. X beta actually can be viewed as v. So in binary logic model, what is the probability of y equal to 1? E to the v divided by 1 plus e to the v. Right? That's the binary logic model. Right? That's the probability, right? So that's the probability of success. So because binary model, there are only two alternatives, 0 or 1. So that's basically, it's also a choice probability. It's the probability of this alternative 1 being chosen. It's modeled equal to this. Now, is this similar to this? Right? If you normalize the v for alternative 0 to 0, you exactly get it. Is that clear? So the binary response model, you have two alternatives, right? Alternative 1 and alternative 0. So binary response model basically is just, as we can see, it's just that for alternative 1, we can say v, and for alternative 0, we normalize to 0. And then the choice probability for y being chosen, for alternative 1 being chosen, is simply, you know, like we said, e to the right? This is our, according to our multinomial choice probability. But then, if the first one is v, but the second one is normalized to 0, it's just like that. And then e to the power of 0 is just 1. So we just get that. This is the binary choice probability from the binary logic. So this sense, that's why I said in the beginning, right? So the binary logic model, binary response model can be viewed as a special case of our discrete choice model. So binary logic model from the binary response model, it can be viewed as a special case of this multinomial logic model. Right? You basically simply just normalize the utility from one alternative to 0. As a matter of fact, you can further derive that if we take the difference between two errors, okay, two epsilon, each of which follows this type 1 extreme value distribution. We take the difference between two IID, the random variable, the IID error, right? Each of which follow this type 1 extreme value distribution. Then the difference is still a random variable, right? It's another random variable. And this random variable, what distribution does it follow? Logistic distribution. All right, so very nice. So basically, the logistic distribution, the binary logic model, which we could derive there, basically simply just assume this error is like the difference between the two alternatives. And the 0 alternative is normalized to 0. The utility is normalized to 0. That's the nature of that binary logistic regression. Is that clear? So basically, it's how the binary logic model can be absorbed into this multinomial logic model framework. All right, binary logic model, you have two alternatives, right? Alternative 1 and alternative 0. So we simply normalize the utility from alternative 0 to 0. And then the epsilon, that error in the binary logic model. In the binary logic model, we simply model the probability from choosing that success, from that the success alternative, from choosing that alternative 1. So then the error in that binary logic model is simply the difference between alternative 1 and the alternative 0. And that difference is following the logistic distribution. Okay, and we can show that if the logistic distribution is a result of the difference from two iritants, each of which following this extreme value distribution. So very nice result. Completely absorb, completely subsume this the binary logic model as a special case. All right, so that's why we want to introduce all those frameworks to you so that you know how things all fit together. Right, so they all come from a very coherent, very self-consistent theoretical framework.
Quick question, yeah. Just curious about the choice probability. So at this point, we submit the choice over the one dimension. So what if, for example, our human being, like our utility, we make a choice over time and over space. So then, whether the result will still hold if we add the temporal spatial component, make it 3D dimension, that still hold.
Yeah, you can extend that. This here, the choice is certainly, the basic version, the choice is like a static decision. Right? Among all the choices you are presented, then you make a decision. But of course, you can extend the model into like a multi-period. Then in each period, you'll be faced with this choice. Of course, then as time goes by, the choice set can change. Right? So today you are faced the choice, from this 10 items. And this 10 has its attribute. But next time, there may be a different items, and the attributes, the x values will be different. Yeah, of course you can do that, but then you need to organize the data, properly, and then you be able to do it. But the basic structure is the same. But just every time you're presented with different options with different x variable values, and then as a result, this v will all be. You can add the time dimension as well. So it's v will be vijt. Right, vijt involve like xijt. So, but the x variables value at a different different time period will be different. So as a result, the vijt will be different for different t values. Yeah, of course you can do. And again, in practice we do. If you have like a so-called panel data, right? You have the data across over different time periods, then you can extend more. But the choice structure at any point of time, right, is always the same. All right. Everybody clear? So make sure this is the essence, this is the core of this the multivariate logic model. All right, the discrete choice model. The choice probability, where it comes from, what's the theoretical framework, and what's the key assumption. All right, so and why it works this way. So make sure you understand that. But again, if you forget about everything, make sure you remember this. All right, so this is the core, this multivariate logic model, the choice probability. And it's equal to this. It's very easy to remember. Basically very intuitive. The e to the utility, right, for the chosen alternative compared to the sum of that e to the utility from all alternatives. And that ratio determines the probability of that utility being chosen. And the binary choice model is a special case of this model. All right. That's the basic setup. Now, before we talk about the estimation, let's think about the so-called very important so-called identification of this model. Now, think about that. I have, say, j different alternatives, right? And I have the utility function specification. So let's say if I add a common constant to the utility of all alternatives, will that change an individual's choice decision? Right? Uij. Right? In Vij, right? So this epsilon ij is a random variable. Let's leave it alone. So Vij. So, but if I add a common constant to Vij of all alternative j's, will that change the choice probability? It doesn't matter. Why? It's the difference that matters, right? When you do the choice, you compare the utility from two alternatives and see which one is larger, and you make the choice. So if I add a common constant to the utilities of both alternatives, then it doesn't change the comparison result. It doesn't change the difference, right? If Uij is greater than Uij prime, after adding the common constant to both U, the Uij is still greater than Uij. All right. So the common constant actually doesn't matter. You can add any constant to all utilities of all alternative specific utility. Then the choice decision will be the same. The choice probability will not be affected at all. So what does that mean for us? Then be careful. That means, think about that. In Vij, what we usually will model is beta 0. Like that. So we will have an intercept. But this intercept is alternative J specific. Each different alternative will have a different intercept. Will have a separate intercept to be estimated. But now think about that. The intercept for alternative 1 and the intercept for alternative 2, intercept for alternative 3, can they all be identified? Given the same data, given the same, observed choice probabilities, can I estimate beta, the intercept for alternative 1, intercept for alternative 2, intercept for alternative 3, and all the intercept for all alternatives? Can they all be separately identified? The answer is no. Think about it. If I have a set of beta values, okay, let's say this is the estimated value. Can I add a common constant to all of them? Yes, certainly you can. Right? So it's just like adding a common constant to each alternative's Vij. So then it will not change the data observation. It's not will change the choice probability at all. So as a result, there's no way you can identify all the choice, all the intercept at the same time. So how many intercepts can you identify from the data? J minus 1. So one of them cannot be identified. So one of them has to be normalized. Usually we normalize to 0. All right, once, for example, we normal the first alternative's intercept to 0, and then we can estimate all the other alternative intercept. But pay attention here, the intercept here, what does that mean? It's not the absolute value. It means the relative value compared to this baseline alternative whose intercept is normalized. Then how does the intercept of the second alternative differ from that? Same thing, how does the third alternative's intercept differ from that of the first one? All right, for the alternative specific intercept in Vij, we can only identify J minus 1 alternative specific intercepts. One of them has to be normalized to 0, simply because of the fact that not, a common constant can be added to all utilities alternatives, and that will not change the choice decision at all. All right, that's the thing. Another thing, think about that. Can the scale, does the scale matter? Yeah, let me finish this part. Does the scale matter? For each utility, Vij, if I multiply that utility by a common constant, will that change the decision, the choice decision? Will not. Again, the choice decision is based on the comparison, Vi1 to Vi2. Right? If Vi1 is greater than Vi2, then if I multiply both Vi1 and Vi2 by a common constant, a common positive constant, it will not change the comparison result. So that's why we can multiply any common constant to all the utility functions, and it will not change the choice probability at all. So as a result, that means the scale of all those parameters, all those beta parameters, cannot be identified. You can easily scale that up or down. You can scale all beta coefficients up and down at the same time. It will not affect the choice decision. So again, in return, based on the choice decision that we observe in the data, we will not be able to identify the scale of all those beta coefficients. All right. So when we cannot identify the scale of beta coefficients, what should we do? again, normalize, fix the scale of the beta code. Alright, so the good part is for normalization, it's done automatically because when we assume the extreme value distribution, the scale is already normalized because the variance of extreme value distribution is, I showed you it's equal to that pi square over 6, that particular constant. So the scale of the distribution is already normalized. So that scaling part is automatically taken care of by using this standard multinomial. So we do not worry about that. What we need to keep in mind is that you cannot have all the alternative specific intercept. You can only identify up to j minus 1 alternative specific intercept. One alternative specific intercept has to be set to 0. Okay, and all these j minus 1 alternative specific intercept is actually measuring the difference compared to that baseline. Okay.